Good afternoon, everybody. Welcome back to Dynamic Optimization. I think we can right away take off where we left on Thursday, where we learned or where we finished the first exercise on Jane's car rental, an exercise we will be coming back to in a couple of minutes. And what we learned was some optimal behavior, and we have seen that the optimal behavior there was, even after a long period of learning, was rather noisy because some states we didn't observe at all, and thus we didn't get a change in the value function for these states, and we didn't get much updates or many updates of the policy in these states. So what we've seen is a rather noisy policy function, whereas the value function was pretty smooth, or at least it looked pretty smooth in the end. What we do to obtain this result was to follow the policy we are learning while we are actually learning the policy. So we didn't distinguish between a policy that might help us explore the state space and the policy that will help us to exploit the state space, so the policy we want to learn in the end. And that's what we're going to do today, to cover up the whole topic on non-approximation reinforcement learning, so reinforcement learning within finite state spaces. So what we have seen in the end then of last week, that we can distinguish between two policies: the policy we want to learn, the optimal policy, or at least a policy that is very close to the optimal policy. And we denoted that by pi in the very beginning of this lecture part. And then we introduced in the last week another policy, so the policy B. So let's fade to the slides. So we denoted the policy we want to learn by pi, and the policy we use to actually learn the optimal policy, we denote this with B. And B is our behavior policy, and this is the policy that determines what we are going to do in the next with our next action. So what our next action is actually going to be. Then we've seen that we needed to adjust the rate that we are learning at, so the alpha parameter that we've set in advance, with respect whether we are exploring, so whether we're following a non-optimal or at least a non-greedy action, or whether we are following a greedy action, because in both cases we need to compute the importance sampling ratio, and that comes from, as the name suggests, from importance sampling. So sampling from parts of a distribution to get an expectation of extreme parts of the distribution with the help of another distribution. So with the help of this behavioral policy in here, which is of course nothing else than a probability distribution, because we're defining the probabilities here for an action given a state. And then the importance sampling ratio is the probability of choosing an action in our policy we want to learn, so our optimal policy pi, divided by the probability of choosing that very same action in our behavior policy. And we can see here that two kinds of actions can be chosen. First, the exploiting action, the greedy action that has the highest reward, or the exploring action that does not have the highest reward. And according to these rewards, of course, the probabilities are higher or lower. So consider the case where we choose the action that gives us the highest reward. Then the probability pi would be very close to 1. The probability B is also rather close to 1, doesn't need to be that close to 1. So for example, B might be 70% and pi might be 99.5%. So with a very high probability, we would choose the greedy action in our pi policy, but in the behavior policy, we choose the greedy action with a lower probability. And then this ratio here gets 1 divided by 0.7, so it's larger than 1. So we increase the weight of learning in each step that is greedy. So each time we choose the optimal action, we learn more than we would with on-policy learning. And each time we choose to not use the optimal action, then this pi here would get very small, so 0.005 for example. B also gets smaller, but of course B has a larger deviation probability, so this gets 0.1 or something. So the whole division here is much smaller than 1. So every time we do, every time we use a non-greedy action, we will learn less from the reward from this action, because that's an action we actually don't want to learn from in the end. And as a necessary condition, we have seen that we need coverage, so we need to have the behavior policy needs to have positive probabilities wherever our policy we want to learn has positive probability. So for example, if we have two greedy policies, if pi and b are both epsilon greedy policies and b has a larger epsilon, then coverage is fulfilled and this condition holds. And we've already seen how we could include that into our SASA algorithm rather simply by computing rho by this ratio here every time, then multiplying rho with alpha every time. And of course, we need to then not just update our policy we want to learn, but also the behavior policy B. So we need to update two policies in each SASA step instead of single policy update. So that's more or less the only difference within SASA, and we will see, you can see that in the exercises in a couple of minutes.
Just, Andreas, just one question concerning the choice of B. Importance sampling means that we oversample certain areas which are normally relatively unlikely to occur, but which are important. So we try to oversample those areas if we do, say, Monte Carlo integration or something. And as far as I know, there are some optimality conditions, so that there is a certain oversampling scheme which is optimal to, say, compute an integral. Is the same available here? Is there any theoretically optimal choice of the behavioral function B?
I actually don't really know.
And is there any intuition which kind of behavioral policy might be a good idea? I mean, we could just choose any action randomly without really updating B. Would that be a good idea?
That, I think it very often depends on the exercise in question. So if choosing a completely random policy, choosing an action completely at random leads to a state that, in the end at least, or in the medium and long term, leads to states that are completely irrelevant for the problem, but just theoretically might happen, then this is not a good idea. So I would suggest using epsilon greedy policies here with a larger epsilon, so at least 10% or something, so that you deviate rather frequently from the optimal policy, but go back to the optimal policy with a large probability. So you explore more of the state space, but not every point of the state space, but only points close to the region of interest, so to say.
Mm-hmm. Okay.
I also have a question, maybe a more fundamental one concerning this importance sampling. Again, I'm not too familiar with that, to be honest. The idea was, as far as I know, is suppose you want to calculate the expected value of an unknown distribution. You sample out of the distribution, okay, then you find something, and then you said, okay, I want to oversample areas that are less likely to occur, right?
Yep.
But at ante, you do not know which areas are less likely to occur because you do not know the distribution, right? This is part of the learning process? So you would sample, you would, I don't know, draw, you would take a sample of 10 realizations, then you would look which one is less likely, which realizations are less likely, and then you would like to sample more often there. Is it something like that, or I'm totally misleaded?
No, it's not like that. It's just a more general, because we are not sampling states actually. What we're doing is we sample actions. And based on these actions, we get a state in tomorrow. And we can, of course, either sample always the action that we think is optimal and that leads to some state, or we can just switch and sample non-optimal actions more frequently. That's the idea, the connection to importance sampling. So the actions that wouldn't be sampled in a greedy scenario will then be sampled. So in other words, of course, in importance sampling, you of course need to know both distributions, at least in the sense that you can compute the distributions or the densities. You need these.
No, I was just wondering, in the general case of importance sampling, you say, I think, as I said, I'm not too familiar with that. It's a concept from statistics, right? So could you briefly recap what that means? I mean, not in this context, but in general, so I could relate it.
In general, if you, for example, want to compute the expectation of a normal distribution in the area that's larger than the 90.9% quantile. If you want to do that by Monte Carlo, you would sample 1 million observations from this normal distribution. Only very few of those are in this very small area. So your expectation is based on a very small number of cases. With importance sampling, you would draw from another distribution that has much more probability mass in that area, and then weigh each of the observation of this auxiliary distribution with the importance ratio in order to obtain the expectation. Okay?
Okay, thank you.
Okay, we can more generally, because we have now seen one single algorithm, so SARSA, we can, of course, introduce different algorithms, and mostly different algorithms means different update rules, but we can also characterize the whole spectrum of what we have seen so far here by the length of the update or the width of the update. If you consider back the dynamic programming approach, then each step of learning included included the expectation of the value function of tomorrow, so the whole value function as of tomorrow, but only as of tomorrow. And on the other hand, on the bottom left corner, we can see Monte Carlo methods where we only considered in each episode a single, in this case, string of events in this single episode, but we considered the whole episode from start to the end. And in temporal difference learning, what we have just seen, in each update step, we only are interested in one set of events regarding just one period in time. And on the very bottom right corner, you can see that you could also go through the whole scenario as of today, look at the expectation, look at all the values that might happen tomorrow. Depending on all these possible values tomorrow, you go to all the possible values the day after tomorrow, and you will end up in exhaustive search. This image is just to give you a little more of a clarification of how differently these algorithms might look and how differently the update steps might look, because we're now coming to a few more additional algorithms. We're not going through them thoroughly, and we will not use them here, but just for you to know that we have seen a single algorithm, SARSA, but there are many, many others one might use in order to learn the action value function and the optimal policy. One of the oldest is the so-called Q-learning, and this one looks, I think, much more familiar because it incorporates the maximum operator here than maybe the algorithms we have seen. This is much more incorporated, this incorporates much more the idea that we have seen in the Bellman equation, because we are updating our action value function with respect to what would be the real optimal choice in tomorrow. Still, after each step, we are going to sample what we are going tomorrow from a policy pi that is, in a sense, that not necessarily needs to be the optimal greedy policy. What we have seen is a one-step SARSA algorithm. So we only updated, or we only decided for one action, and after that action was executed, we updated our action value function and our policies directly. We could also do this not with a single step ahead, but we could go for 2, 3, 4 steps ahead, and then base our update not on R plus the discounted value function minus the current value function, but on the reward plus the discounted reward the day in the next day, plus the twice discounted reward the day after that, plus the 3 times discounted remaining value function minus a current value function. So this is a little more, might be a little more stable than, again, also depending on the current setting and scenario we are in. We can also, instead of using the future bootstrapped action value, because when choosing a future action, we only look at one possible action. We could also compute the expectation of tomorrow's action value function, then with respect to the policy of the state we are in tomorrow. And instead of using the actual realized action value tomorrow, we can work with the expected action value function. This is the expected SARSA approach. So a bit more stable, a bit more using expectations instead of every time just a single observation or a single realization. But of course, depending on the scenario, this is more, of course, more computational intense. And we can mix those with the n-step Q sigma algorithm. So where we have an alternating combination of n-step SARSA and expected SARSA. So we have an expectation step where we update with this expected SARSA rule, and we have an n-step, or at least or one-step, in most of the cases, SARSA, where we update just according to the regular SARSA approach. These two, this mixture then very often, or some, depending on the scenario, gives quite nice results. So the cyclist in a maze example in the beginning was solved with the n-step Q sigma SARSA. So working much smoother and much faster than the regular SARSA, which actually wasn't really able to finish this problem in a decent amount of time. Nevertheless, we are not going through all these algorithms. If you want to implement them today or in the next sessions, you can, of course, do so in the exercises. The Jane's car rental example is, I think, a very good example, or a very easy example, because the scenario is very easy to implement these algorithms. So if maybe we're going too slow for some of you, and if you want to experiment with these algorithms, just try them, and you can find all these algorithms in algorithmic notation in the Sutton book. And you might directly copy the ideas from there and apply them to your code if you'd like to. That being said, I would like to start the breakout sessions, unless there are questions, of course, with the Jane's car rental exercise part 2. That is just incorporate a off-policy learning methodology. So are there any questions? All right, then let's start. Okay, welcome back. I think implementing this change from the first solution of Jane's car rental to the off-policy learning solution of Jane's car rental is rather straightforward, because we only add a new policy, update that policy as the other policy, and we're basically done. And in this very setting of the car rental, off-policy learning does not improve the behavior that much, because the reward that we obtain tomorrow it depends slightly on what we are doing today, but because both the rental requests and the returned cars are IID first, and secondly, more or less independent of our action, we won't gain that much by deviating from the optimal policy. Nevertheless, though, And there are slight differences in the policies that we end up with, and a little bit of in the value function we end up with. I just recalculated or resimulated the car rental example here with not with a maximum of 10 cars, but with a maximum of 25 cars per location. So, and in the bottom row, you can see the result of off-policy learning, and in the bottom row, you see the results of the on-policy learning. In this case, we have a very high epsilon in the off-policy, so I think it's around about 50% or something. I don't recall it right now, but it's a very high value for the off-policy, for deviating from the optimal policy. And the two important differences you can see is that even after a very large number of iterations here, we didn't fully encounter the state space in the on-policy learning, but in off-policy learning, we at least have seen 99% of the state space at least once, which is sometimes good to know, but in this case, of course, we will never have 25 cars in the second location if we are not going to put cars every evening from the second location to the first location. So unless we do that, and that is very, it's a very, for our business, of course, a very bad thing to do because we lose money. We are not really that much interested in the upper parts of the value function anyway. And as you can see regarding the optimal policy, that seems to be at least a bit less noisy regarding the bottom right corners. So we would much more know what to do if we ended up with lots of cars in the first location and only a few or even many cars in the second locations. And also this area in the bottom left corner where we more or less don't do anything is a bit smoother than in the example with on-policy learning, but we do not really gain much with off-policy learning in this very setting. Nevertheless, this setting is, I think, a good introducing idea of going from finite state spaces to infinite state spaces, because as you can see here, the value function we get, and especially the policy we get, is already relatively noisy. First and second, the state space, though rather small, so it is 25 times 25 times 11, so not such a huge object, but a larger object than the first one where we only had 11 times 11 times 11 potential state action combinations. We can see here that if we increase the size of our car rental, we wouldn't be able to solve this anymore. Or if, for example, we didn't only have, if we, for example, thought about that the rentals of today are a autoregressive process, so the rentals of tomorrow depend on the rentals of today. So we have, for example, a seasonality in summer or something like that. Then not only would the number of cars we would have in the locations be a state, but also the rental requests at both rentals would be additional states, because these determine then what the rental requests will be tomorrow and so on. So then we had more states, which would give us an even larger object. Then it's not only 26 by 26 by 11, but 26 by 26 by 26 by 26 by 11 would then be the size of our state space. That is then something we cannot really work with exact solutions, because we cannot at all, even if we only look at the important parts of the value function, look at enough parts of the value function. So we need something, or to come up with a solution to switch from representing each point of the value function in an object. So each possible state has its own value inside this potentially very large object, and we need to get from this to an approximation of the value function. So what we are going to do now is we leave the countable set of states behind, and now we work with continuous states and hence continuous value functions. And these do not necessarily need to be continuous state spaces. We can, of course, have a very large car rental, up to 500 cars in each location. We couldn't do that anymore with a discrete or with a discrete state set, and we couldn't store this in a very large array, or we won't store this in a very large array, but instead we go to continuous methods and we approximate the value function, and we approximate, maybe approximate depends on how much time we have, the policy. We have used approximations before when we talked about the expectation of the value function, and when we, if you remember the approxfun command in R, when we approximated the value functions, even in the deterministic case, between different points of our states. So we already did that, but we did it in a black box approach because we didn't really need to know what was happening inside the computer in order to get this to work with the dynamic programming at the beginning of the semester. Now we turn a bit to different methods of approximating the value function. And to do that, we need to work with a little more in terminology, because with approximated value functions, we can, of course, not update the value function at a certain point, because we no longer have any object that says, okay, this point of the value function cube represents 2 cars in the first location, 2 cars in the second location, and the action of I shift 1 car from the second to the first location. We do not any longer have such a representation of the value function, so we can no longer work with updating each individual element of such a cube or a hypercube if we have more than just 2 states and a single action. And we do this now by we do this in the end of this session and in the next session by, in the end, using neural networks to do that, or using any kind of function approximation on the first hand, and we store a number of weights, a vector of weights, which will be used inside this function, which will be later on an actual R function that represents our value function. And this vector of weights, or this collection of weights, will then be used to compute something based on the states, and this then will represent the value function. How exactly the approximation of the value function works, we'll see in a couple of minutes. But for now, this vector of weights, W, will represent everything we need to know about the value function. And then the value function V hat is then the value function of a certain state with this vector of weights W. So this is an approximate value function, and this one is differentiable with respect to to W, with respect to the weights. So for example, you could think of V hat here as a regression, a linear regression. Then if you take the derivative with respect to one of the weights, that'd be possible. We denote by Q hat of S and W the approximate action value function. Again, this one is differentiable with respect to the weights. And with nabla, we denote the gradient operator, so the vector of all the partial derivatives of a function with respect to the weights. In our case, of course, we're interested in nabla, in the gradient vector of either the value function or the action value function, because we want to find out in which direction do we need to change the weights in order to increase or decrease our value function later on.
Just a brief question concerning the notation. The Q hat, doesn't it need an additional argument for the action?
Sure, sorry. There is an A missing here. So this is Q hat of S, A, and W. Yes.
I also have a question, sorry, concerning the, just for me to recap this. So basically what we had before, now what we did recently is we had this Q object, so the action value function object, which consisted of all possible states and the according actions that you could choose within these states. So it's a collection, potentially a large collection of many numbers, depending on how many states there are. Okay. And now what we are doing is we try to approximate this. But what I do not understand, I mean, if you have the Q hat as a function of all the states and all the actions and this way vector, don't you then also have a large collection of many numbers depending on all the states and all the actions and all the ways? I mean, is it how helpful is
no,
that?
it's not necessary. What you are doing is you approximate the value function by this, first of all, abstract vector thing, in order to not need to store a number for each state combination. So for example, if you consider what we did to initialize the value function in the Jane's car rental, there we just said value function is 380 plus 10 times cars in the first location plus 8 times cars in the second location. This is just a linear approximation of the value function. This would be one possible approximation of a value function, in this case a super simple approximation, because we're just saying, okay, the value function is linear in the cars in the first location, it's linear in the cars in the second location. That's obviously rather unrealistic, I think. For most applications, of course, it's unrealistic that this linear approximation would hold. And in this case, we would have a vector of just 2 weights. The weight for the state 1 is 10, because we have 10 times the state 1 that determined our value, and the weight for state 2 is just 8. And we would have a third weight, the 380, which is the constant here. So we would represent the value function, at least in the way we initialized this in the Jane's car rental, with a vector of 3 different weights.
I see. Let me try again. So instead of having super many pairs of numbers, you just represent all those super many pairs of numbers with a function, and you still have all the different states and the actions, but that doesn't really matter because you do not need to store or code with super many numbers, but you have this function. This is basically what I mean, from a theoretical point of view, you would always use a function, right? So you would never work with super many number pairs or digit pairs, and this is basically what you here replicate. You're saying, okay, look, just I decrease the size of the object that I'm looking at by a conceptual approach, which we could call a real function. Is that what you mean?
That's, yeah. And we actually didn't use a function. We already used a large number of numbers, so a large set of numbers.
But we call it action value function,
that's true.
right?
Yeah.
Because
okay, so instead of using this whole cube, we could also use just a set of parameters, so to say, and have a functional form here in the value function, and we will, in the subsequent hours, learn how to update this functional form representation, or at least the parameters of this representation, to gain information on the value function, and with that, of course, on the policy. Most of the times, we are not only interested in the bare states themselves, so the number of cars in the first location, the number of cars in the second location, but we might need to create a feature vector from these states. We can do this in several ways. We'll see on the next slide. If you just consider back the car example, then we had and the initiation of the value function. We could, of course, add some interaction term to that initialized value function. So the number of cars in the first times the number of cars in the second times 0.1 or something might be also a factor that might affect our value function. So what we need is then, or what we need to learn is first a vector of weights. We will learn these with the same or similar algorithms that we have seen so far. And we might need a way of creating features from our state space, because we're mostly not interested only in the direct states, but also in their connection to each other, in their or in nonlinear effects from the states. So let's just briefly talk about the approximation methods. So the simplest one is, of course, a linear approximation. And in this case, that's what we just did in Jaynes car rental, where we had the weights vector multiplied with our features. In this case, the features were just the states. So very basic, the more or less simplest approximation method. And then, of course, the gradient of that one would be just the features that we derived from the states. We can also do this for the action value function by saying that we derive the features not just from the states, but from state-action combinations. Let's have a brief look at some methods of creating features. I'll just show you these for completion. We are not going to use these in the next week, but nevertheless, I think it might be interesting to learn about them a bit. We might construct features from polynomial bases. We can have, if we have a k-dimensional state space, we might want to index that, or we might want to map that into an n-dimensional feature state. And we do this by selecting the lth feature being the product of our state to the power of some coefficient. So for example, we can create a constant here by saying that CLJ is 0 for all else that are for all j for L equal to 1, then the first feature would just be constant. The second feature might be that C to 1 is 0 and C to 2 would be 1, then we would extract the second state and so on. So these would be the features we could have created when initializing the Jaynes car rental value function, but we can also work with all the interaction terms here. We can add quadratic terms, quadratic interaction terms, and so on. So we have a polynomial basis in n dimensions based on our previously k states. And if we use this nonlinear feature construction with linear approximation methods, we would obtain the gradient of that one very easily, and later on we'll see that we need the gradient to learn, so it's a good idea to have a very easy to compute gradient. And we can at the same time include potential nonlinear features of the state space or of the value function regarding the state space. What we have already seen, or at least used in the dynamic programming approach, is grid approximation, where we said that, or where we might have said that everything between two grid points has every points in between have the same value. Or one could use the so-called coarse coding or tiling, where we have in this case, in this example, a two-dimensional state space. And we are not taking just a single grid, but we take different overlapping grids depending on the current location of our point. So this gray point here, this gray point would activate different cells of these 4 grids. So in each of these grids, one of the cells would be active, and the weight that is attached to this active cell would then, or the sum of the weights of the active cells would then be a representation of our value function. So these 3 methods are just there for completion. Next session on Tuesday, we are going to start with artificial neural networks, which is, I think, it's a very general and a very nice nonlinear approximation method. And you will see how to use those to try to approximate the value function. And we will first do that with some toy examples, so you get to know to use the code in R for that. And then again, we are going to apply these neural networks to the Jane's car rental situation. So, are there any open questions for today? Then I'd say we see each other on Thursday and have a nice week until then.
I got a organizational question. So today they will publish the exam dates for this exam period, and I would ask if you already know what is the exact time period where we will work on our
We are quite
assignments.
flexible regarding that. We wanted to make that more or less up to you, so that you have no exams that interfere with the DIN-OPT exam. So I think we can talk about that on Thursday when everyone has looked up his or her dates. And then I think on Thursday or next Tuesday we come up with a solution to, I think, when our exam is going to be.
All right, thanks.
All right. Then I think let's see on Tuesday.